So let's recap what we know about eigenvectors. So imagine we have a linear transformation given by a matrix A. So as you know, this linear transformation takes in a vector v and it produces a vector A times v. Now, there are some special vectors called the eigenvectors, which, when inputted into our transformation A, what we get is a scaled version of the original vector, lambda times v, where lambda is a scalar called the eigenvalue, and v is called the eigenvector. And each eigenvector is associated to a certain eigenvalue. So actually, if we write it mathematically, what we can say is that A times v, which is the output vector, must equal lambda times v. And this is the mathematical definition of an eigenvector and its eigenvalue. So why are eigenvectors important? Well, the eigenvectors are telling us valuable information about the transformation. Okay? So for example, imagine you are doing a rotation in 3D. So you have your axis, x, y, z, and then you have a transformation which is rotating space around a certain axis. Okay, so this axis might be tilted somehow like that. Yeah. So our rotation is rotating maybe by 90 degrees or something like that. Well, clearly the vectors whose eigenvalue is equal to 1 are vectors that end up the same as they begin before the rotation, right? Because A times vector v equals 1 times vector v. So they end up unchanged. So lambda equals 1 will have eigenvectors which will be equal to the axis of rotation. So every eigenvector with an eigenvalue equal to 1, for this case of the rotation in 3D, will be the axis of rotation. Okay? So it's giving us important information about the transformation. Now, imagine a transformation which is a projection in 2 dimensions. And for this, I have the applet. So this matrix here was taken from a previous problem, and it corresponds to the projection of a vector v onto a line with slope m. Yes, you remember this. So by changing vector v, you can see that we always get A times v is equal to the projection. So what will the eigenvectors tell us for this transformation? Well, the eigenvectors whose eigenvalue are lambda equals 1 will be any vector in the line of projection, because A times v equals 1 times v. So the vector v is unchanged. So this is telling us about the line of the projection. Yeah, very clearly. Now, what about the vectors that are not in the line of the projection, but the vectors that are perpendicular to the line of projection? So all these vectors here that I'm sliding through right now. So notice that A times v is equal to 0. Therefore, all these vectors will be eigenvectors with an eigenvalue equal to 0. So let's write that down. Vectors with lambda equals 1. So eigenvectors whose eigenvalue is equal to 1 will be vectors that are parallel to the line of projection, while the eigenvectors with lambda with eigenvalue equals 0 will be vectors that are perpendicular to the line of projection. What about this next example? Mirror symmetry around an axis in 2D. So let's have a look at how this would look like. Consider this matrix here, 0, 1, 1, 0. So this matrix is getting every vector v, and it's doing like the mirror symmetry, as if this line, this dashed line here, was a mirror. Okay? So now what could you tell me about the eigenvectors with lambda equals 1? Once again, any vector within the line of mirror symmetry will be an eigenvector with eigenvalue equal to 1, because the output is equal to itself. And any vector that is orthogonal to the mirror symmetry, like these vectors here, this will also be eigenvectors. What will be the eigenvalue for this? Think about it for a second, if you want to pause the video and think about it. So clearly these eigenvectors will have an eigenvalue of -1, because A times V is vector V flipped, so multiplied by the scalar -1. So let's write that down. The eigenvalue lambda equals 1 will be associated with eigenvectors which are parallel to the line of mirror symmetry, while the eigenvalue lambda equals -1 will have eigenvectors associated to vectors that are perpendicular to line of mirror symmetry. So as you can see, in general, when you calculate eigenvalues and eigenvectors for a certain transformation, it is very likely that you will get an insight as to what this transformation is actually doing. Okay? Thanks for watching.